non-multiplying systems of different geometrical sets are of utmost importance. So, for solving the transport equation, for a given assembly, you can have your transport equation in appropriate coordinate x or fx. So, what type of coordinate terms you are accustomed to? One is Cartesian coordinate system. There is your x, y, and z axis, and I cap, j cap, and k cap. Then your polar coordinate system, r, theta. Then your cylindrical coordinate system. There is also components like your phi, your z, and your r. Similarly, your spherical polar coordinate system, r, theta, phi. So, to express transport equation, you have to choose appropriate coordinate frame of reference. In its general form, the transport equation for a non-multiplying system can be written as 1 by v del by del t of phi is equal to minus omega dot del plus omega dot delta plus summation plus sigma, which is a function of e whole multiplied by phi, which is a function of r, omega, e, and t, plus integration 0 to infinite d dash multiplied by integration 4 pi d omega dash sigma subscript s phi plus s. So, for plane geometry, slab of finite thickness with infinite transverse dimensions, you have your angular flux, which is dependent upon one spatial coordinate only, and you can write it as omega dot del phi is equal to phi subscript s del by del x phi. For an infinite slab, you have to choose the polar coordinate system so that its axis is along the x-axis for expressing the angle-dependent neutron flux, which would be symmetrical for rotation about the x-axis and independent of azimuthal angle. So, what is azimuthal angle? Anybody? Azimuthal angle क्या है? Am I audible?
Yes, sir.
So, what is azimuth?
Sir, voice is not audible, sir.
ହଁ am I audible now? ତାହେଲେ କୋଉ ପର୍ଯ୍ୟନ୍ତ ହେଇଥିଲା? I think I am being disconnected. So up to which part of this transport equation I was be audible? प्लेन ज्योमेट्री वाला आपने देखा या नहीं था? डिस्कनेक्ट हो गया था. Am I audible?
Yes, sir.
प्लेन ज्योमेट्री वाला
Sir.
कहाँ से डिस्कनेक्ट हो गया? Plane geometry, spherical geometry, cylindrical geometry.
सर मेरा प्लेन स्फेरिकल से मैं डिस्कस हो गया था सर.
Spherical के बाद ठीक है. So let us discuss cylindrical geometry again. So you know, in cylindrical coordinate systems, you have components like Z, R, and phi. So for simplicity, we can consider an infinite assembly. This leads to the fact that the space and angle dependence of neutron flux would be determined by the radial distance r from the axis of the cylinder, the angle between omega and z axis, and the angle between the projection of omega on the plane z is equal to 0. Z is equal to 0 represents a plane which is perpendicular to the z axis. And xy, it can also be said as xy plane, and the radius vector in this plane. Thus, we may write the transport equation for cylindrical geometry as 1 by v del by del t plus 1 minus mu square root over cos omega del by del r minus sin omega by r del by del omega plus sigma phi is equal to integration 0 to infinite d dash integration 0 to 2 pi d omega dash integration minus 1 to 1 d omega dash sigma subscript s phi plus s. Am I audible? Am I audible? Okay.
Sir.
Then we may discuss the integral form of transport equation. So, the integral form of transport equation can be solved analytically for neutron even for complex assemblies. So, we can write the integral form of transport equation using the method of characteristics, wherein linear partial differential equation is converted to an ordinary differential equation as 1 by v del by del t plus omega dot delta plus sigma phi is equal to q. So two partial derivatives you encounter. One is del by del t of phi, another is omega del phi. So del by del t phi and delta phi, these are the two partial derivatives, and it is equal to a total differential for an observer traveling with neutrons. Am I audible?
Sir.
Okay. So you can write dr is equal to v omega dt, which is equal to omega ds, where your ds is equal to v dt. And your s is a measure of the distance along the path of the neutron. The solution can be written as a characteristic curve of the transport equation as r vector is equal to r0 vector plus s omega vector, and your t is equal to t0 plus s by v. So your r0 vector and t0 are constants of integration. So you can rewrite this equation as a linear first order differential equation d by ds plus sigma phi, which is a function of r0 plus s omega and omega e, which is equal to q omega e. So this equation can be integrated easily by introducing an integrating factor in both sides. Okay, so in the previous class we have discussed Pell's equation and constant cross section approximation. So let us move to the next part, your diffusion equation. So the basic assumptions are the neutron flux is only weakly anisotropic, the double differential scattering cross section is azimuthally symmetric, the time rate of change of neutron current is much less than the collision frequency, and neutrons from fissions and external sources are emitted isotropically. Then we can derive the diffusion equation. So we can recollect in the previous class where the most general form of neutron transport equation is 1 by v del by del t omega plus omega dot delta plus sigma phi is equal to integration 0 to infinite d dash integration over 4 pi d omega dash sigma phi plus q. For a multiplying assembly, neutron source term will be of the form q is equal to 1 by 4 pi xi p 1 minus beta f phi plus sigma j xi j lambda j cj plus s. So you can integrate over omega and you can have 1 by v del by del t plus sigma phi plus del j is equal to integration over 4 pi d omega integration 0 to infinite d dash integration over 4 pi d omega dash sigma, where phi is the sigma phi plus q, where phi, which is a function of r, e and t, is the angle integrated neutron flux. So your phi is equal to Vn, which is a function of r, e and t, which is nothing but integration over 4 pi phi d omega. So you can recall from the previous class that angle integrated neutron current J is given by integration over 4 pi J d omega. So angle integrated source term is also Q is equal to xi p 1 minus beta f phi plus sigma j xj lambda j cj plus s. So this can be further simplified by using the fact that for azimuthal symmetric, double differential cross section depends only on the product of angles. That is, your mu 0 is equal to omega dash omega and not on individual angles. So you can write integration over 4 pi sigma s d omega is equal to 2 pi integration minus 1 to 1 d omega 0 sigma s, which is nothing but sigma s r comma e dash to e t. So you can interchange the order of integration over omega and omega dash and rewrite the results as 1 by v del by del t plus sigma phi plus del dot j is equal to integration 0 to infinite d dash sigma s phi plus q. So your neutron diffusion in terms of angle integrated neutron flux and neutron current can be expressed beautifully. So we can solve phi and j or otherwise have a relation connecting these quantities. For this, we can multiply omega x and integrate it over all angles. This will lead to 1 by v del by del t plus sigma jx plus integration over 4 pi omega x omega vector del phi d omega, which is nothing but integration over 4 pi d omega omega x integration 0 to pi d dash integration over 4 pi d omega sigma phi plus qx. So here qx is equal to integration over 4 pi d omega omega x q. So your q dash is a unit vector and the product q omega dash omega is equal to 1. So you can write the scattering term as a is equal to integration over 0 to infinite d dash integration over 4 pi d omega dash integration over 4 pi d omega omega x sigma s sigma dash sigma dash phi. So your sigma dash dot sigma dash is equal to sigma x square plus sigma y dash sigma x dash square plus sigma y dash square plus sigma z dash square. So if we take all three directions as equivalent, then on an average you can write omega dash dot omega dash vector is equal to 3 omega dash x square. This helps us to write the expression in for azimuthally symmetric neutron scattering. And your expression will be a is equal to 3 integration 0 to infinite d dash integration over 4 pi d omega dash integration over 4 pi d omega omega x dash sigma s multiplied by omega dash x phi. So the term with the bracket can be written as integration over 4 pi d omega x dash sigma s is equal to 1 by 3 integration over 4 pi d omega omega dash sigma s, which is nothing but 2 pi by 3 integration from 1 to plus from minus 1 to 1 d omega 0 mu 0 sigma s, which is nothing but 1 by 3 sigma s1, and your sigma s1 is the first moment of the double differential scattering cross section. So the scattering term takes the form A is equal to integration 0 to infinite d dash sigma s1 integration over 4 pi d omega dash x phi, which is equal to 0 to infinite d dash sigma s1 jx. So you can use this expression and have the equation 1 by v del by del t plus sigma jx plus integration over 4 pi omega x omega del phi is equal to 0 to infinite d dash sigma s1 jx plus qx. So your similar expression can be written for y and z components of j, and you can combine all of these three and have the equation of the for neutron current as 1 by v del by del t plus sigma j plus del dot integration over 4 pi omega dot omega phi d omega is equal to integration from 0 to infinite d dash sigma s1 j plus q1. For isotropic expression of neutrons from a source, we can put q1, which is a function of r, e and t, is equal to 0. In order to further simplify the second term of the left side, we use P1 approximation for angular neutron flux as phi is equal to 1 by pi phi plus 3 by 4 pi omega dot j. Using this relation in conjunction with the following relation, integration over 4 pi a dot omega d omega is equal to 4 pi by 3 a vector. And your integration a dot omega b omega d omega is equal to 0. Now the second term of the LHS simplifies considerably. Del is equal to integration omega phi d omega is equal to 1 by 3 del phi. On combining these two equations, you can have the expression 1 by v del by del t plus sigma j plus 1 by 3 del phi is equal to integration over 0 to infinite d dash sigma s1 j vector. So we assume that the rate of change of current per unit current is much less than the collision frequency. So you can write 1 by modulus of j vector multiplied by del by del modulus of j vector is very smaller than v sigma. On combining the equations, you can have your j is equal to minus d del phi, where d vector, which is a function of r, e and t, is equal to 1 by 3 sigma minus integration of 0 to infinite d dash sigma s1 j vector divided by j vector. So this is nothing but the space energy and time dependent diffusion coefficient. So your r vector represents space, e represents energy, and t represents time. So your sigma is a function of RET, d is a function of RET, your j is a function of RET. So this expression is nothing but your space energy and time dependent diffusion coefficient. Okay, am I audible?
Yes, sir.
Okay. Then we can discuss initial and boundary condition. The solution of diffusion equation involves a lot of arbitrariness. In order to obtain feasible solutions for a given problem, certain initial and boundary conditions are imposed upon. Also, let us discuss the initial condition. At a given time, the energy and space distribution of neutrons must be known. Usually, you consider the origin of time as the reference point, and this defines the initial condition. If phi j, which is a function of r and e, space and energy, If the initial flux at T is equal to 0, we may write this condition as phi is equal to phi j for all R and E. So if we discuss boundary conditions, you can impose boundary condition on flux phi, which is a function of space, energy, and time, are quite similar to those imposed on the wave function while solving Schrodinger equation. But you can also deal this with a physical quantity, and therefore the neutron distribution in space represented by phi, which is a function of r, must be either 0 or positive and finite elsewhere. Since diffusion equation is a second order differential equation in space coordinates, its solution will involve two arbitrary functions. Hence, two boundary conditions for each variable would be required. However, the physical solution must be real and non-negative, as well as finite everywhere. Apart from this, symmetry of the problem must also be satisfied such that phi x is equal to phi of minus x. In a slab with x is equal to 0 being the center of the slab. So the usual boundary condition would demand that at a material interface, flux and current are continuous since such interfaces are devoid of sources or sinks. So, what are the boundary conditions? Free or non-reentrant boundary condition at the interface between a material medium and a vacuum, where you can have your extrapolated boundary as shown in the figure. In y-axis there is phi x, in x-axis there is x, and you can have a linear extrapolation having extrapolated boundary. Okay, so your xd is equal to xs plus 2d, 2 capital D, which is equal to xs plus 2 by 3 lambda tr. The boundary at this distance of 2 by 3 lambda tr is called extrapolation. Are you getting it? Then source conditions. Source condition can be fixed in such a manner as to ensure that when infinitely close to the source, the total number of neutrons emitted by the source equal the product of neutron current and the surface area. For a point source which emits S0 neutrons per second isotropically at r is equal to 0, this implies that limit r tends to infinite 4 pi r square j vector is equal to S0. So your 4 pi r square signifies the surface area of a sphere of radius r drawn around a point source. So you can consider a plane source located at x is equal to 0 isotropically emitting S0 neutrons per unit area per second. So this will give condition limit x tends to 0, jx is equal to S0 by 2. So the net neutron current at the origin on either side of the source plane is 1/2 of the total source length. So diffusion equation is reasonably valid for normal systems. However, in regions close to a neutron source or near the boundary of a scattering medium or for a heavily observing medium, the diffusion equation may not be valid and the assumptions made in driving it may not be valid. However, for a medium which is not highly observant or is one or two mean free paths away from the localized source or a boundary, it will lead to physically accepted results. This allows the diffusion theory to predict the behavior of the neutrons well and solve the equation rather easily. Okay. So this is all about diffusion equations. You can go through the worked out problems. Are you getting it?
Sir.
Okay. So next we can discuss the last part of the course, and that is am I audible?
Sir.
Okay. So we have discussed the last part is last part of the elements of reactor physics is one speed diffusion equation 1, one speed diffusion equation 2, two group diffusion equation, then finally the critical equation. Shall I discuss it today or tomorrow? This is the last one, and the course will be completed.
Sir, tomorrow.
Tomorrow we shall discuss diffusion equations,
Sir.
such as one speed diffusion equation, two group diffusion equation, and the critical equation.
Sir.
Okay?
Sir.
So thank you for
Thank you,
your
sir. Welcome,
patience
sir. Thank you.
listening. Okay?